Welcome back, compadres. Today we're going to do some FEA post-processing on the connector forces that we pulled out of our FEA model in the previous video. Specifically, we're going to look at joint integrity. So we're going to look at bolt bearing and shear tear out. These are two criteria we often evaluate as engineers when we look at designs. So let's go ahead and step into it. So what I have here is I have a calculator that determines our margins of safety for shear tear out and bolt bearing. And the inputs are the following: joint thickness, nominal diameter, the fastener going into the clearance hole diameter, the edge distance, some allowables, some temperature knockdown factors, safety factors, bearing factors, and then my loads multiplied by a force multiplier. So I use this when I'm doing a linear analysis, so that if I run a simulation and I get a result and then the loading conditions change, increase or decrease, I can still salvage my model by just including this multiplier and multiplying it by my loads. This is only for linear analysis though, so beware. So what we did in the last video is we pulled out connector forces for 4 elements. Here's my 2 shear loads and then my axial load. So we're just going to run through an example calculation to demonstrate how to do this. So let's look at element 3. So the first thing I want to do is go into my model here, and then I've gone into the visualization module right here. I go to my display group, go into my element item, my element label method, and then I want to put in that element 3 and then highlight it. So this helps me find the location of my fastener. So now what I do with this information is I go into my CAD model and I actually get the geometrical information I need to put into my calculator. So this is my geometric model of that component right here, and you can see here if I orient it correctly, what you're going to find is that this thing is symmetric, and element 3 would be this hole right here. So what am I going to need for my calculator? Well, let's go ahead and measure it. I'm going to need the clearance hole diameter. So my clearance hole diameter is 0.1015. So next I need to determine my edge distance. So my edge distance, I'm just going to choose the shortest edge distance. And you can see here for my edge distance calculation, I need to go from the center of the hole to the edge. You can see here that doesn't work out right here. So what I do is I'll click use as axis on that surface, and it'll give me the minimum distance there of 0.364. So let's check the other edges here. 0.35, that's smaller. Let's check the other edge. 0.35. So my smallest edge distance is 0.35. I'm going to be conservative and use that value right there. So now once I have that, we need to look at our joint. And so we can see it's a single shear joint. If you recall, a single shear joint is essentially when you pull with one load on the top joint, you get the same reaction load on the bottom. So what we do next as a FEA analyst, we kind of use some common sense. We want to evaluate the thinnest member. That's going to be the weakest member or the weakest length. And so what we would do next is we would measure the thickness of both these joints. So that top joint is 0.2 inches, and then the bottom joint, if I can click it, it's going to be 0.25 inches or 1/4 of an inch. So that top joint is the thinnest, so that's going to be the weakest. So we'd want to use a value of 0.2 for that top joint. And then the diameter of this hole, we looked at it already, but a number 2 fastener would fit in there. That's what I'm going to assume in this case. So if we go into our Excel spreadsheet, we can go ahead and put in our inputs, and I've already filled it out ahead of time, so we wouldn't spend much time doing that. But what you'll find is that if we go through our inputs, put them all in here, then we go into our calculations. So we take our shear loads and we multiply it by our multiplier. In this case, I'm assuming 25G. I carry that down, calculate an equivalent shear load using Pythagorean theorem. And then I calculate my E over D, which is used to basically help calculate our bearing ultimate and bearing yield values. And then I calculate a bearing area, and then I calculate our margins of safety for bearing right here. So I calculate an ultimate load using a safety factor of 1.5 and a bearing factor of 2, and then I calculate a yield using a 1.15 factor. And so we've seen this calculation steps in a previous video, so I'm not going to go into it, but basically what I've done is I've interpolated values based on E over D, and then I've knocked down those values with a temperature factor as shown here of 97.3% for ultimate in this case. So I've taken into account temperature, and then I go into calculate my margin of safety, and then I do the same thing for shear tear out. I apply a temperature knockdown factor to the joint I'm looking at, the material, calculate a shear area, and then calculate a margin of safety. And so we can, say we want to look at 40 G's. So I'm going to put 40 as our force multiplier, and it'll change our margins of safety. As you can see, they're still positive, and if they're positive, they're good. Checks the list, we move on. But you can see we do this for each element. So what I've done here is I've gone through and done it for each element in each joint, and you can see this is kind of how I would lay it out. I just take this calculator approach, and then I put it into columns. That way I can extend it down and calculate a value for each joint. So that's what you'd want to do as a structural analyst. So you want to do something like that. And so I got my element number. So each element is going to have 2 joints, so I got to do 2 calculations. I have number 2 fasteners. The material is aluminum. I label the part, the load type, because it can change if I'm doing vibe, and then that's going to change my multiplier. And then I put in my thickness values for each case, my clearance hole diameter, and then my geometric properties. We fill that out. And then we go through and put in our joint allowables. This depends on the material we're looking at. My temperature knockdown factors, and then my safety factors, bearing knockdown factor. And then we put in our shear loads from FEA that we pulled out, and then we apply our multiplier. In this case I'm applying 10. We can change that. I multiply that multiplier by the shear load, and then I go through calculating equivalent shear, and I do the same calculation steps. I apply my temperature knockdown factors, calculate my shear and bearing areas, and then calculate my margins of safety here. So that's kind of the approach that I use when I do anything. So I start in Excel, and then I go through and make a calculator, and then I extend that calculator to columns where I can calculate everything at once. And so I hope that provided some insight into how to work as an FEA analyst and also joint calculations. So I'll see you next time. Adios.